Hi, my name is Jennifer Bertrand. This paper is about using a webcam and a mouse cursor to learn about how people interact with digital objects. We approach this from a movement neuroscience perspective, exploring the dynamic patterns of the visual and motor systems during naturalistic digital object interactions. Previous research has examined non-digital object interactions and how the visuomotor system makes this happen. With tech advances in measurement tools, this research has evolved to more natural, self-paced, and realistic tasks, like Land and colleagues' tea-making task. Two key takeaways about object interactions emerge from these early works. One, the eye gaze falls on task-relevant objects only, even ignoring highly salient objects in the scene. And two, in general, the eyes lead the hands by about half a second. Recent advances in technology have made it possible to quantify visual motor patterns with even greater precision. Previous work from my colleagues at the University of Alberta has confirmed and refined the consistent patterns of eye-hand coordination during real-world object interactions. In this case, they found that all object interactions involve the eyes fixating the object at least 500 milliseconds prior to the start of the interaction. Within 600 milliseconds of the interaction start, the eyes would leave to look ahead to the next area for fixation. The visuomotor dynamics of digital interactions has been explored to some extent in the lab with more rigid paradigms, and to a much lesser extent in realistic or ecologically valid contexts within the HCI domain. In general, when present, the eye-leading hand pattern is observed on the magnitude of about half a second, but measuring and assessing the temporal features of visuomotor coordination in meaningful ways is yet to be fully realized in HCI studies. Webcam eye tracking is one potential solution to capture more natural and realistic digital behaviors in a person's own environment. Recent advances in deep learning approaches and consumer hardware quality have improved gaze prediction algorithms for webcam eye tracking. However, there are still limitations and challenges to using webcam eye tracking. We aim to overcome these challenges and explore whether we can collect data during digital interactions where the participant is in the comfort of their own environment using their own device. This fits nicely with the human-centered design principle of considering the user, environment, and context in which their experience is happening. We had two primary motivations. First, a methodological motivation, to explore if the quality of the webcam gaze data and subsequent processing procedures would be sufficient to explore visuomotor coordination in our specific task. And second, an empirical motivation, to quantify if the patterns of eye-cursor coordination would match principles of eye-hand coordination in the real world. 51 participants completed the hour-long experiment, and 29 datasets were remaining after data cleaning. In terms of our study's materials, we used LabVanced, an online experimentation platform, to build our study, which offered mouse cursor tracking and webcam eye tracking for our browser-based experiment. We recruited remote participation using Prolific, an online crowdsourcing platform. This was in service of our goal to test the utility of webcam eye tracking when collecting data from participants in their own environments and with their own hardware. In service of our other, more empirical motivation, we designed our task as an approximation of Lavoie and colleagues' real-world task. Participants were shown a picture of the real-world task and told that this was a screen-based version. Instead of cups, participants dragged and dropped circles across the screen between 4 target locations, or areas of interest, AOI. Each trial involved a sequence of 8 movements, i.e. 8 drag-and-drop interactions. The circles were always dragged laterally, where near circle was moved between the near AOIs and the far between the far AOIs. Participants were thoroughly trained on this sequence with interactive instructions. We describe in a lot of detail the methods of this work in both the paper and its supplementary materials. We spent almost 1 year designing, building, and then rigorously pilot testing our experiment to get remotely collected, high-quality webcam eye tracking data. I want to get to the results, but I'd love to answer some questions about the methods at the end. We begin our results with what's effectively a sanity check for the quality of the webcam eye tracking data and its processing treatments. Part of this data processing involved a k-means clustering approach to bin the gaze data into the 4 spatial areas of interest, AOIs, of the task. For this first result, we wanted to know if our webcam eye tracking data showed the expected pattern of participants looking at things that were relevant to the task at the appropriate times. What I mean by that is, for each of our 8 movements of the task, there would be 2 AOIs that were relevant to that movement because they were a pickup or drop-off location, and there would be 2 AOIs that were irrelevant to the movement. We can ask how much time on average was spent fixating AOIs when they were relevant or not, collapsed across all 8 movements, and we get the expected result of significant differences in looking time driven by task relevance. We complemented this time-based result with the spatial assessment of our gaze data too. This is described in detail in the supplementary materials, but in brief, we can calculate bivariate probability density functions for each AOI to assess the spatial specificity of our data, and in short, find the data to be noisy but not in a way that puts us at risk of misassigning gazes to the wrong AOI. I'm going to go through these next results step by step because there's a lot packed into this one figure. The first thing we wanted to look at were the durations of the movements. Remember, there were 8 self-paced movements in a trial. We used a segmentation strategy similar to what has been used in the real world to break up the trial into 8 movements and then each movement into 3 parts: reach, transport, and release phases. Transport is the dragging of the circle from the pickup location to the drop-off location. Here, we see the average duration of each phase across the 8 movements. While there are some slight differences across the phases between moves, the big takeaway for us is how short the transport phase is relative to the other phases. This is a departure from real-world findings, but not that surprising given the dramatic change in task space. Of course, we were most interested in what the eyes are doing at these times. What you're seeing here is what we call eye arrival latency, EAL, at pickup. This shows how much earlier the eyes arrive at the pickup location before the pickup happens. What we think is pretty remarkable is that with webcam eye tracking, we are able to show a consistent anticipatory look to the pickup location about 500 milliseconds before the cursor gets there for the interaction, which aligns really nicely with real-world findings. Next, we can look at the eye leaving latency at the pickup location, the black dot, as well as the eye arrival latency at drop-off. In general, these both behave as expected. The eyes leave the pickup at about the time the pickup starts, and then the eyes shift to the drop-off location, arriving there in what seems like as soon as possible after a successful pickup. Finally, we see the eye leaving latency at drop-off. We think this result is super interesting. What you're seeing is that the eyes stay at the drop-off site for quite a while after the drop-off happens. In fact, it's about 500 milliseconds more. What's interesting here is that in the real world, the eyes at drop-off look just like pickup, where they arrive 500 milliseconds before and leave right around the moment of drop-off. But in this digital context, using a cursor instead of the hand, the transport is so quick, around 200 milliseconds, that it isn't possible for a 500 millisecond anticipatory fixation to the drop-off. Instead, there's some compensation for the abbreviated transport so that the eyes still get 500 milliseconds of fixation on the object. Returning to our motivations, we were able to demonstrate the utility of webcam eye tracking as a method with this work. However, as we endeavored to explore realistic gaze from remote participants, by necessity we had to give up a lot of experimental control. This translated into numerous limitations to our method, and we describe these in the paper. In terms of our empirical motivation, we were able to demonstrate intriguing eye cursor coordination patterns that reflected both flexibility and preservation in relation to real-world patterns. We caution readers to take these results as preliminary given the methodological limitations. There are a number of interesting design and research implications for the user experience domain, and again, we elaborate on these in the paper. In sum, we have demonstrated the promise of remote webcam eye tracking for user-centered visuomotor research with encouraging, though preliminary, findings about gaze behaviors during digital interactions. Thank you so much for watching.